Swayam Prabha. Digital India. Educated India.
Morning, welcome you all for this next lecture in this particular course on analytical, spectral and microscopy applications of inorganic compounds and some nanomaterials as well. So, we have so far looked at some techniques like general introductions, then atomic absorption, then we looked at the chromatography. Now, let us look at another important and very interesting topic on the thermal analytical methods, which is nothing but thermal analysis on this. So, this will go for this class, maybe a couple of more classes as well, wherein I will be introducing all the techniques, some principles, how it functions, what one can get out of that, or some kind of an applications and the examples, which is very similar for many of these topics that I will be talking in this particular course. Okay, so thermal analysis, thermal techniques, thermal analytical techniques, it does not matter, all these terms will come to the one and the same. So, I will be focusing on four important topics of this. One is thermogravimetric analysis, other is differential thermal analysis and differential scanning calorimetry and isothermal titration calorimetry. So, we will go in detail in each of these techniques, understand what we get out of the, what information do we get out of this and what we can conclude out of this, how we can analyze the sample. So, all of these will be a part of this particular course under this particular kind of a topic. Okay, let us look at the one of the techniques, that thermogravimetric analysis. How do we understand the word thermo and then gravimetric? I am sure everyone knows thermo means temperature, thermal, thermally related, all of these terms comes into picture. Gravimetric is, I am sure many of you must have done gravimetric analysis in your early college days or high school days, etc. Gravimetry is something to do with the mass or weight of the sample. So, it is the thermal and it is the weight. So, now you can understand that it is a technique which is dependent on your temperature and on your weight of the sample. So, that means you keep changing the temperature and keep weighing the sample, therefore, you can get what kind of a weight. Is the weight is constant, is the weight is changing, weight is decreasing, weight is increasing. So, many kinds of things can happen. So, that is what you are going to measure. So, how does it happen? That looks like a physical parameter. No, it is not true. It is because of the physical and chemical processes that undergo when you heat the sample as a function of course, temperature and what will happen. So, when you take some sample and heat, then you forget about the atmosphere. If you are doing it outside, air will be there. If you are doing inside, what kind of an atmosphere that you are maintaining. So, it is the mass or the weight, the temperature, and the temperature can be changed over a period of time at a particular rate. That is what is called in terms of time. So, I start at room temperature, I go at a rate of 10 degree per Celsius per 10 degrees Celsius per minute. That means, in the next minute my temperature will be the 25 plus 10, the next minute will be 25 plus 10 plus 10, etc. So, that is what you call in terms of the time. So, time itself monitoring will also show the temperature variations of this. Okay. So, as I said that if you are doing outside, it will be air, you can do inside a chamber with certain kind of a atmospheres, and therefore, these atmospheres can be inert type like nitrogen, argon, these kind of things. Or at times you will use purposefully the reactive gases or reactive atmospheres, reactive surrounding. So, that could be air. In the air you have oxygen. When you are heating some sample, oxygen will, you know very well, will add to the heating part of it, and which is referred as combustion. I am sure every one of us have studied at the early stage of the school the combustion process. So, and it can be done in some atmospheres like CO2, ammonia, O2, all of these kinds of things. Many more atmospheres as you may require for your sample, you will use it. And that can, when you are using that atmosphere, you can also have another parameter called the pressure, at which pressure you are using. So, all of these. So, that means you have a weight of the sample, you have the temperature, rate at which the temperature is varied, the pressure at which that you are doing, and what kind of a atmosphere you are using, whether it is a non-reactive or whether you are using a reactive kind of a thing. So, all of these will make the thermogravimetric analysis more useful, more interpretable, therefore, the analytical results will be important to that. So, hope that the basic principle is is conveyed to you. So, if you understand the basic principle, and to support that, I have shown here a diagram which talks about what components are present in this and what you measure, what you do, etc. So, you have a furnace because you want to heat at a particular. This furnace has to be controlled with some electrical wiring, so that you can control the rate at which the temperature can be varied. And then how do you know? You have to use the recording of that, and then you also need to measure the weight of the sample. So, you also need to measure the weight of the sample. So, therefore, the weight of the sample to measure, you obviously require a balance. So, you connect it to a balance, and then if you want to controlly use some atmosphere, obviously you can close this one. So, this whole chamber can be closed. So, this whole furnace can be put into a chamber, and then sample will be inside that, and sample is heated using this furnace at the rate at which you want and to the temperatures to extent what you want. You may start at the room temperature, you may go up to 500, you may go up to 700, you may go up to 1000. So, whatever be the thing is. So, even beyond, not only just 1000 is not the limit. So, it is beyond also. Okay. So, that means you will be pumping some kind of an atmosphere into this, and otherwise air, otherwise you can do it under vacuum also, and you can do it under inert atmospheres too. You will not do under vacuum because the gases come out will be sucked by the vacuum. So, you will use under inert atmosphere. So, and either you will use under a inert atmosphere, you will use under a reactive atmosphere, and this is where what you will be doing. Okay. So, I hope this you understand. You have a furnace, you have a controller, the temperature controller is called programmer. Okay. What rate you want, to what temperature you want, where you are starting, all of these things can be made. And as you keep heating the sample, you will have a change in your weight, and that weight you are connecting to the balance, and this will give the balance reading, temperature reading. All of these things are taken, and there will be a computer that will control all of these, the temperature, the weight, all these kinds of things. And the atmosphere can also be controlled by the computer to say, if suppose you have 3-4 different cylinders, you can switch over cylinder. So, one containing oxygen, other containing CO2, other containing N2, other containing NH3, anything. So, you can also do that. So, entire control is possible. Those are not shown in this figure, because that does not mean that they are not controllable. So, you have today machines available with all kinds of those things. So, what is that a simplistic way? Either you can plot the temperature, the time on the x-axis, or the temperature in the x-axis, or the rate of as a function of times, and on the y-axis what you have weight. So, you have certain weight you started with, then next weight, the next weight, the next weight, etc. Now, if you look at this on the right top example is showing for thermogravimetry analysis, is in the short form referred as the TGA, and this TGA. So, you see that you are increasing the temperature on the x-axis, and you are looking at the weight. So, 100 is the percent, that means whatever you have taken in the starting, you call it as 100%. So, the weight is there, and as you keep increasing the temperature, you can see there is a little bit of lowering, little bit of lowering, little bit of lowering, but there is a sudden drop. There is a sudden drop between this temperature and this, and then again very minute kind of a change is there. So, what you can say, there is a small change in the weight over a temperature from the room temperature up to about 600 plus degrees Celsius, and beyond that you have another sharp kind of a change in the temperature you have. So, that is where, So, this is a very sharp temperature change that you are looking at. So, this will convey certain information because there is certain kind of a mass change. The weight is changed from somewhere from 100%, then the first part will be around 94-95%, then this has come to about 55% or so. So, the difference will be the 55 versus 95, that will be around 40%. So, that will give you some information which I will explain you in the later slides. So, that itself is a information. So, you may say it is just a weight loss. No, there is a lot of things one can convey based on this. Okay. So, this is for, so what are these? We are going to study in the later slides. Another example is shown here. Mainly we have one basic step, sudden drop between 650 and 750, there is a sudden drop is there. So, we will also, I will also give you a method how exactly we can find at what temperature this transition is taking, that also I will be explaining in a while. Just hold on your breath on that. This is another example, again calcium, but not carbonate, it is a calcium oxalate. So, here you see one drop here, second drop here, third drop here. So, the three. So, there are three major weight losses, that means three major processes happening. So, here there is one slow process and one sudden process. Here three sudden processes, one here, one there, one there. So, of course, I will also tell you exactly what are these, etc., when we go later on. Right now what you require is, so is a thermogravimetry analysis can give you the weight loss steps basically. Let us look at on the next slide, will basically give you the temperature versus the weight or weight loss. So, the temperature versus the weight, thermogravimetry. So, and this is you plot here as a function of temperature versus weight percent. So, initially you can take as 100 obviously. So, how it is happening? So, there is no change here, there is a change here, there is no change in this region, and there is a change here, etc., etc. So, from here to here there is no change, from here to here a sharp change, from here to here almost no change, from here to here is a sharp change, etc. Each of these will convey. This particular thing is called thermogram. So, you will find the weight loss steps, and this is the thermogram which is big. Now, how do I find exactly what temperature this loss is occurring? So, what will I do? I will, if I call this as a weight or a mass, some books will use as that, does not matter, temperature. So, what you will do? You will make a derivative of this. So, you will make a derivative, that is d of weight by d of temperature, not time, temperature. This is it. You can convert into time also because you are controlling. So, you will get somewhere here and this and this, something like that. So, this is the temperature you can make at T1, this you can make at T2, etc. So, at T1 something is happening, sudden process, and how much is the weight loss, that we can find from the T. This is called the TGA curve and this is called the DTG curve. So, that is differential thermogravimetry, and this is thermogravimetry analytical curve. So, that is where these are. So, this is just by you do not need to do any experiment for this. This is just only derivative. So, is a mathematical. So, once you get the TGA, you automatically get the DTG. So, it is just a mathematical conversion of that, and that is what you say. So, so here in this example you can say there is one drop here, there is a second drop here, there is a third drop here, and the slopes may or may not be very smooth, and that you will see when you do the derivative. So, this dash curve is a derivative. You can see that looks very nice, one. So, therefore, there is only one, but when you look at here, there is one small turn point, there is another small turning point and a main peak. So at those things some processes are going on, different kinds of losses you can, and then here nothing is there, and then when you come again here, so therefore you can get the temperature here. So that will be for that process, temperature for that process, whatever the small reaction occurring, you can take that temperature, you can take the temperature. So this dash curve is the DTG curve, which does not require additional experiment, only the same experiment of TGA gives you the DTG. So many times people are not very clear about that. So where all one can use this? So I have still not explained you one more part, how to interpret this, that we will come in just in a while. So all that I have shown you is the principle, how it is done, what you get, what is a thermogram, what is a differential thermogram. This can be done for organic things, can be done for the materials, it can be done for polymers like thermoplastics, thermosets, elastomers, etc., paints, so many things, so many samples, food samples also, forensic samples, all of these you can do the TGA. TGA requires experiment, DTG does not require additional experiment, same experiment you can use it just for deriving. So it is just a mathematical function which is so this DTG is nothing but dW by dt versus T, and the TGA is the weight or weight percent versus T, temperature or whatever the temperature profile kind of thing. Can it be used for the inorganic? Absolutely, absolutely. A lot of examples of inorganic compounds we will be looking at, catalysts, materials, many kinds of things can be used for food, synthetic materials, etc. So therefore in this case, what are the parameters you can use? Temperature. I can do it very fast temperature variation, I can do it a small temperature variation, very slow change in the temperature. I can use oxygen, I can use nitrogen, I can use argon, I can use CO2, the atmosphere. So all of these things, then I can follow it up. So and then so therefore the rate of the heating obviously will also have influence on the resolution, how well each of these peak, this drop, this drop, this drop is. If they are close by and if you are going at a fast rate, you will not be able to resolve these steps, and that is what is called the resolution. And if you are not able to resolve these steps, the accuracy will be obviously lower. So the better the resolution, the better the accuracy that is. I hope now you understand the basic principle, the instrumentation aspect of it, the process and the thermogram, all of those. Okay, now we are coming into the examples. So these are the applications as well as example, whatever you take. So here is one which is nothing but the calcium oxalate 1H2, it is synthesized in the lab and that is there a crystalline product. Now you put into the TGA machine and then start working on it, and this is done in a inert atmosphere. It could be argon, it could be nitrogen, anything, it does not matter. So it is done that. So when there is some other non-inert gas is used, I will inform you that time, otherwise you can take it as. So at the inert atmospheric condition, this calcium oxalate water gives 3 peaks, one weight loss, a little bit slope kind of thing, little faster here, another weight loss, another weight loss. So what is on your x axis? Obviously is the temperature, and the y axis is the weight or weight percent. So starting from 100, it goes up to somewhere here, and then it goes up to somewhere here, it goes up to somewhere here. So this is around 35-40. So going from 100 to 40, that is around 60. So you can see 61.7, 31.5 and 12.4. Now what is happening at this temperature is very low, between 100 and 200. So 100 and 200 you can take is granted in most of the coordinated water, most of the crystalline water, water which is crystallized and in the lattice, they are all going. Some cases may be 250 up to 300, but most often between 100 and 200 kind of thing. So you know that this compound has one water molecule, and that is the water which is going. How do we know? So if you check, there is one water molecule for this total one. So if you can find what is the weight percentage of one water out of this, that will come to 12.3, and you can see 12.4% is the one. So how do you work out? You work out here what is the weight percentage, and you find what is the weight, and this difference, this is the weight loss. So, this is the one what you are talking about. For this one, the weight loss is from here to here, this is the weight loss. So, weight loss 1, weight loss 2, etc., weight loss 3. So, this will be 12.3. The next one, if you take this one, and that is calcium oxalate breaks down to carbonate and CO. So, CO3 plus CO, C2O4. The C2O4 gives CO3 plus CO, and that is where the thing is. So, this if you calculate it will be 19.2. Now, 19.2 plus earlier already 12, that will be 31.5. You can see 31.5. So, here it is 31.5. Now, there is one more drop is here, and that calcium carbonate which is there, nothing will happen to CO because it will escape, and the calcium carbonate that cannot escape, and it is a solid material, and this at the temperature when you go to higher, something like 700 to 800, then it will start further decomposing. So, loss of water, decomposition of oxalate, decomposition of carbonate. You are not started with carbonate, but carbonate is formed in the middle. So, you have to take care of that as well. So, and this carbonate will further break down to calcium oxide plus carbon dioxide, and if you take this weight percentage, it will come to 30. So, this is 30, this was earlier 31.5, so 61.6, totally you can see 61.7. So, now you got the process, the whole thing. Now, this is a characteristic, these temperatures are very characteristic. If they shift, that means there is some impurity, there is something else is there. You can also find from the weight losses whether something else is also added to this. So, all that you can analyze the compound characterization, you can analyze the compound purity. So, you can characterize the compound as well as the purity can be established. So, these are all of these are possible here. Okay. So, I have another example on the right side, it is a copper sulfate 5H2O, which is a very known thing. We know that copper sulfate loses water in 2-3 different steps, etc., all those things, and then whatever is a colored bluish becomes pale greenish or pale colored one, etc., etc. So, we know that we studied early stage as well. Now, we are looking at using the TGA. So, here also this curve with the steps is called the TGA curve, and the curve with the peaks is called the DTG curve. Now, here there is one step here, the second step here, there is a third step here. This difference between the temperature is very small. First step immediately, second step happens not with some gap, and then third step with a gap, and then there is a fourth step, fifth step, like this. So, you can see how nicely the DTG curve. So, that means you are taking a derivative, that is dm by dt, or you can call dw by dt, it does not matter. So, here you have the temperature. So, if you take the derivative curve, you get the two peaks. So, the first loss is at this temperature, second loss is at this temperature, and both correspond to this. First loss is 2 molecules of water, second loss is another 2 molecules of water, not same 2 molecules of water, because totally 5 molecules of water is there. When 2 are lost, 3 molecules left. These out of these 3, again 2 molecules is lost, and then one more molecule that will be lost. So, all this will happen within 200-300 degree Celsius, as I mentioned. Now, you have percentage is also worked out. You can sit down and then do the percentage workout, then you will understand that. So, you have 2 molecules at one stage, another 2 molecules another stage, another 1 molecule another stage, totally 5 molecules of water. Now, only your compound gets affected by the temperature. So, when you go beyond 800, so beyond 700, so 700 plus 750 to 850 or 900, actual decomposition of the copper sulfate is happening. So, whatever is happening before that is a water loss. So, you have seen. So, the first 2 molecules, next 2 molecules, next 1 molecule. So, totally 5. So, so all this. The 14.5. So, 14.5, 14.5, 29, and the next one is 1 molecule. So, there will be half of it. So, it will be around 7. So, 29 plus 7, and that is around 36, you can see that. So, that means 2 molecules of water, 1 molecule of water. Then after 700, 750, you will start seeing again the decomposition. Again in 2 steps, and you can see that step 1 and step 2. So, you have this is breaking down copper sulfate into copper oxide, sulfur dioxide plus 1 oxygen. So, the reason for the 2 peaks in the range of 700 to 900 degrees Celsius is temporarily it forms, you know that when it when the copper sulfate breaks down, so you have copper oxide is there, okay, and also there is a the unreacted copper sulfate is there, and in the next step, so this will come SO2 plus half O2 etc. This copper oxide and this can also combine. So, tentatively that copper oxide plus copper sulfate kind of an adduct. So, that is called adduct. So, at that temperature that adduct is formed, you are not started with, and that is why you get 2 of them. So, one breaks down at a little lower temperature, other one will break down at a higher, because this is in the adduct. What is coming out is from the copper sulfate. The copper sulfate directly will give here, copper sulfate with copper oxide will give here at little higher temperature. So, there will be little higher temperature from here to here around 50-60 degrees Celsius higher. So, that is where. So, straight copper sulfate will break at a little lower temperature, copper sulfate for copper oxide the adduct will break at a little higher temperature. So, you could see the step 1, the step 2, the step 3, and then these are if you take 2 steps, is a copper sulfate with copper oxide, copper sulfate, copper oxide adduct breaking down again back to the sulfur dioxide and oxygen. Those are the things that you can. Okay, another example I have shown here, the calcium acetate. You look at here. So, it would have been better if they have written in the case CaOAC, the calcium acetate. So, acetate you know very well is nothing but CH3COO, that is what is acetate is, and this with the calcium. So, that is about calcium acetate is. In the previous case it was oxalate, in the previous case it was carbonate, all those kinds of things etc. Now, this one there is a small weight loss here around 200, and then up to 400 there is nothing, then 400 to 450 something, but then 450 to 500 another small, and then up to 600 nothing, again 600 to 650 or 700 750 there is again another drop is there. You can see that the weight loss. So, this is a calcium acetate from synthesis. When you make, you get with the XH2O. Okay. So, that is what it is. So, how do you fix the X? You can fix this X by measuring the weight loss here in the up to 200, 250, this one. So, from here to here this is a 5%, this is a 5%. So, 150 to 240, that is what is here up to here, and that is 5%. If you calculate the 5%, then you will get, I think you get something like 2.2 moles or something like that. So, you will get that particular one. Okay. So, that is where you have the water is being present. Then you have calcium acetate, this is done in air, and then so once the water is gone, then the acetate gets affected. So, in the acetate here will give the carbonate, because the oxygen is available, air means oxygen is available. So, therefore, that will give you the CO3, and then what will be the loss from the acetate? It will be acetone. So, you getting from acetate you will get carbonate. So, this will give you calcium carbonate plus acetone, okay, because oxygen is available from that. So, you have the from the air. So, therefore, you have CH3COO minus 2 of the molecules of that, and that will give you, that will favor the reaction in this direction. You can see that. Okay. And that means you got the calcium carbonate here, and then calcium carbonate will further decompose to give calcium oxide by giving the calcium carbonate. We are going to explain some more examples in the later slides or probably in the next class. So, that will come as the CO, and this will happen beyond 600, 650 up to 750. So, you can see that yeah. So, these are the weight percentages calculated here from this, not calculated, basically from the experimental values which were obtained and shown over there. So, it is not only this, you can also look at even the mixture of compounds as well in these things. I will explain those things in the next class. So, now we have seen the pure compounds, or pure or with some impurity during the synthesis, but not a mixture kind of things. So, we can look at the TGA coming out of the mixtures as well in the next class to come. Thank you very much.